start off with a definition. If n is any positive integer, so numbers like 2, 3, 4, 5, etc., then the principal nth root of a number a is defined to be the following. If we have that the nth root of a is equal to b, this means that the number b raised to the power of n is equal to the number a. So to give you a couple numerical examples, we might say that the cubed root of 8 is equal to the number 2. This is because 2 cubed is equal to 8. 2 times 2 is 4, and multiply that by 2 once more, we get the value of 8. So we can think of taking the cube root here as undoing the process of exponentiating. Of course, the square root is just a special case of the nth root when we have the number 2. Notice that we don't usually put the number 2 here, whereas if we do have higher numbers, we are going to put those values here above our square root. So the square root of 81, we know this is equal to 9, and that's because 9 squared is equal to the number 81. Finally here, one more example, we have the fourth root of 81 is equal to the number 3, and that's because 3 to the power of 4 is equal to the number 81. Let's use this idea to simplify the following expressions if we can. Let's begin here in the upper left where we have the fifth root of 32. Now we know that 2 to the power of 5 is equal to the number 32. So it must be that the fifth root of 32 is the number 2. Now moving over here, we see something new for odd nth roots. So because our nth root is odd, we have the number 5 here, we're actually going to be allowed to get a negative value out of our nth root. So it is true that negative 2, when raised to the power of 5, we get negative 32. So that means here, when we take the fifth root of negative 32, we're going to get negative 2. Next, let's move on down to the bottom where we have the fourth root of 256. So here, 4 to the power of 4, you can check that this is equal to 256. So the fourth root of 256 must be the number 4. Now, what happens when we try to take the fourth root of a negative number? Well, it's not going to work, and that's because there's nothing that we can raise to the power of 4 that's equal to negative 256. So here there's no possible solution over the real numbers. And that's because anything raised to an even power can never be a negative number. However, a negative number raised to an odd power can give us a negative number. So that's why we have this kind of new thing happening with our odd nth roots. And we're going to rewrite this in a different way so that we can think of our nth root as a rational exponent. So we have an exponent that is a fraction. So here we can think of the nth root of a as a to the power of 1 over n. So just to give you an idea with some numbers, let's take the square root of x. We can rewrite this as x to the 1/2. If we have the cube root of x, we can think of this as x to the 1/3, and so on and so on. Using the idea on the last slide to help us out, we're going to define fractional exponents as follows. If we have an expression a, and our exponent is a fraction, m over n, then we can think of this as a to the 1 over n raised to the power of m. And we saw on the last slide that a to the 1 over n, this is just the nth root of a, and then all of this is going to be raised to the power of m. Now, alternatively, we could think of a to the m over n as a to the m all to the power of 1 over n. And we saw that any expression to the 1 over n, we can think of that as the nth root. So it's also possible to think of this particular expression, a to the m over n, as a to the power of m, and then we apply the nth root. So either of these ways to think about a fractional exponent is okay. We can either take the nth root first, and then take the mth power, or we can take the mth power first, and then take the nth root afterwards. Let's go ahead and use the ideas that we saw on the last slide to help us simplify some fractional exponents. So here we have 8 to the power 2 over 3. Now we want to rewrite this using nth roots and powers separately. So remember that the denominator of the fraction of our exponent tells us what root that we should be taking. So in this case, we're going to take the third root, or the cubed root of 8, and then the numerator of our fraction tells us to what power we take our answer to. So in this case, we're going to first take the cubed root of 8 and then square our answer that we get. The cubed root of 8 is equal to 2, and when we square that, we end up with a final solution here of 4. Moving over to the next example, we have 16 over 81 all to the power of 1 over 4. So remember that our denominator tells us what root we're going to take. So in our case, we're going to take 16 over 81. We're going to take the fourth root of this fraction. Notice that because our numerator is equal to 1, we don't take any powers after we're done taking our fourth root. Here we can use properties of nth roots. We can break this up into the fourth root of 16 divided by the fourth root of 81. The fourth root of 16 is 2, and the fourth root of 81 is 3. Now the reason that we define our nth roots and our fractional exponents the way that we have in the previous couple of lessons is because we want all of those properties for exponents to work whenever we have fractions as our exponent as well. Because, it wouldn't really make sense for us to have one set of rules for just integer exponents and then a totally different set of rules for fractional exponents. So just to refresh your memory on some of those exponent rules, if we have the same base, but we have different exponents, say m and n, then we can add together those exponents to get a to the m plus n. So we can do this even if m and n happen to be fractions. If we have the same base and we are dividing, then we can simplify by subtracting our exponents. So here, a to the m divided by a to the n is equal to a to the m minus n. One that we've seen already and we've already used inside of our definition is the following, the power of a power. So if we have a to the m to the n, this is still going to be a to the m times n. So if we happen to have two fractions here, we would just multiply those two fractions together. Let's say we have two expressions inside of brackets, and we raise that to the power of m. Well, we can simplify this expression by distributing m to both of the expressions a and b. So this is going to be true even if m happens to be a fraction. It's probably best if we move on to a couple examples. Know that all of the properties that we have talked about are going to be true, so you can apply any of the properties that we have seen in any of the previous lessons. Let's try to simplify the following expressions using some of the properties that we saw on the last slide. Looking here at our first expression, we have the same base for all three of our terms, but we have different powers. So we have 3 over 5, 2 over 5, and 3 here. Since we have multiplication happening between these two exponential expressions, we can add together the powers. So in the numerator, we're going to get x to the 3 over 5 plus 2 over 5. And I'm going to leave that x to the 3 in the denominator. Adding these two fractions, we're going to get 5 over 5, or just the power of 1. And we saw before in a previous lesson that if we're dividing our exponential expressions, we can subtract the powers. In this case, we're going to take x to the 1, and we're going to subtract off 3 because that's the power inside the denominator. Simplifying, we get x to the negative 2, or we can rewrite this as 1 over x squared. Next up, let's take a look at 8, a to the 4, all to the 2 over 3. Now here we're going to use the distribution property, so I'm going to distribute the outside power, which is 2 over 3, to both the 8 and the a. Now when I distribute to the a, because we have a power of a power rule happening, I'm going to multiply these two fractions together. So we have 8 to the 2 over 3 times a to the 8 over 3. Now I'm going to go ahead and simplify this 8 to the 2 over 3 just a little bit. I know that the denominator means to take the third root. So here we can take the third root of 8, and then when we're done, we can square whatever our answer is. So I'm going to indicate that using these outer brackets. We know that the cubed root of 8 is 2, so we're going to get 2 squared. And 2 squared is equal to 4. So here we have a fairly simplified version. We have 4 times a to the 8 over 3. And I would probably favor leaving it like this and not introducing any more radicals into our simplified answer. Let's go ahead and work through one more simplification. This one's going to be a little bit messier because we have to use quite a few laws of exponents to push this one through. So let's begin by noting that our outside exponent is negative. So we can change that negative 1 over 3 to a positive 1 over 3 by switching the order of our numerator and denominator. So I'm going to move the y3z to the 6 up, the negative 8 y to the 3/4 down, and that has the effect of changing our outside power to positive 1/3. Now that it's positive, we can go ahead and distribute it through to all of the terms inside the brackets. So first I'm going to distribute the 1/3 to the y to the power of 3. So we get y to the power of 3 times 1/3. Do the same thing for z. We get 6 times 1/3 here. Have to do the same thing in the denominator, so we're going to get negative 8 to the power of 1 over 3. And we're going to get y to the 3 over 4 times 1 over 3. So let's simplify some of these multiplications. Y to the 3 times 1 over 3 is just going to be y. Z to the 6 times 1 over 3 is z squared. In the denominator, we're going to think of the 1 over 3 as the cubed root of negative 8. So I'm just going to draw that over here in blue. So I'm thinking about this as equivalent to negative 8 underneath a cube root. And we know that the cubed root of negative 8 is going to be negative 2. So I'm going to simplify that right away. I'm just going to put a negative 2 here in the denominator. And finally, we're going to multiply our last two fractions together. 3 over 4 times 1 over 3. That's going to give us y to the power of 1 over 4. Our final step in this question is we have two like bases here. We have a y in the numerator and a y in the denominator. Our last step is naturally just to subtract the powers of our two y's here. So our denominator is going to remain as negative 2, but we're going to regroup that y to the 1/4 up into the numerator. So in blue, over on the side, I'm just going to show you what's going to happen. We're going to have y to the 1 minus 1 over 4. Now this is the same thing as 4 over 4 minus 1 over 4. So our new exponent that we're going to get for y is going to be 3 over 4. So here is our final simplified answer. All right, my little epsilons, stay positive.